Hi. So we are discussing about the connected vehicle platform and the platform for the performance engineering, which is being integrated with the connected vehicle platform so that we can do the performance engineering activities on the connected vehicle platform where we have the vehicles and a cloud. The vehicles are communicating to the cloud, and how they communicate will show further. If you look at this diagram represents the vehicles which are connected to the cloud solution, and they are having a communication protocol. Right now, we are using MQTT protocol, which is creating a bridge to connect to the cloud, and cloud has its own publisher and subsamplers. Moving forward, the majority of the components which included in a typical connected vehicle platform are device management, which you need to handle the devices, and they are the smart devices. They are already registered in IoT. The IoT is a hub which is always making a connection with all the devices, and they you can communicate to the cloud using those devices. Then we have vehicle data stream, in which we have authentication systems comes, and the device authorizations, like if you suppose you have a device in your vehicle or you have a device in your hand as a mobile phone. If you want to connect to the cloud, then you will be connecting via vehicle data stream. You need to authorize, and then the communication will start, which is called two-way communication, cloud to device and device to cloud. We require data storage as well, because there are huge number of telemetries which are getting communicated from the device to the cloud, even though they are not being used in the real time. For example, suppose if your vehicle has a battery, so battery charging status. So there will always be a telemetry which will be produced by the device to the cloud and get the details of the charging status of the service. Similar way, because the devices should be smart enough to communicate on the services, so we have introduced machine learning platform. We have different applications. They are divided into front-end apps, back-end services, and integration services, which includes mobile APIs as well. Different integration includes apps which are connected to the databases, and of course the customer vehicle billing service policy data. And lastly, we have the mobile apps which the consumer will be using at the end. So you have a mobile app, you want to check the status of your vehicle's various parameters. You can simply send a request which will go to the cloud, and your vehicle has smart devices inbuilt in it which will be communicating to the device and which will be producing the data to the cloud. Going forward, this is a typical data flow where you have a connected vehicle to a end user and how the communication takes place. So if you look at the external system is the end users like us as a customer of that smart vehicle. So we create a request which will go as a command to the system, and of course that will be communicating to the connected vehicle platform, which is a cloud solution. After that, once the gateway will recognize the command is correct, then it will packet it and then again send it further to the vehicle. Vehicle will recognize the command which is coming from the authenticated result. So it will process the request, it will perform the command, and then send the result back. The result will come back to the integrated environment again, and that will be processed. And lastly, the request response will get onto the mobile device which is being used by the end user. So this is a typical data flow. For monitoring, because we have n number of vehicles on the road which are running and they are communicating to a common platform which is a connected vehicle platform. So obviously we have lot of vehicles which are keep sending the telemetries in terms of getting the data to be available at the latest, and in terms of getting connected to the internet and getting, like features like maps, features like, getting the charging status, like getting the data for a lot of firmware updates in the system. For that matter, whenever we are doing performance engineering, we are working on the services to be performance engineered, and to while doing the executions we use push to query language to get the data. So basically a lot of telemetries are getting executed with very high TPS in the application, which gets the data, and which data gets processed using these smart query language, and you can identify at what point in time you have achieved the peak and at what point in time the vehicles were not producing peak volume in the system. So everything is connected, and we are creating a SRE integrations also, so that we can understand the availability metrics of the telemetries which are getting sent from the end users at various different integration points. So moving further to it, we have created a performance engineering framework. And before that, if you look at the screen, it is for the device to cloud communication. So we have the cloud to device communication, and of course after the request or the command is sending from the cloud to the device, then the device will respond, which is known as device to cloud communication. While working on the performance engineering side of the connected vehicle platform, it is very important to have a robust framework for the testing as well, because we are producing a lot of volume, high valued volume in the system, which has various services which are communicating to the system, various devices which are communicating to the system, and of course your vehicle is also getting bootstrapped. So whenever your vehicle is getting bootstrapped, suppose you have 50 million vehicles running on the road. If they are getting bootstrapped at the same time, then it is a high volume of telemetries being communicated, and they will produce a lot of traffic in the system, which will eventually get triggered, and there will be an event hub where all the data will get triggered, and they will produce a lot of volume at event hub. So you need to be very smart enough to understand the data, and out of that you need to find out the availability metrics as well. So just to make sure on this area, we have proposed a performance engineering framework which works on Gatling and other Kubernetes cluster environment. So this is a typical architecture of the framework which we are proposing. So if you look at the left hand side of this diagram, we have an application cluster on the right side, and we have a tool cluster on the left hand side. So basically this tool framework runs on the runner pods, and they are getting spawned based on the number of hits coming from the system. So suppose if we have a production volumetrics with a very high volume of data, then, and the system, the cluster, the test framework cluster, if it is not having enough capacity, so it will auto scale, and it will auto scale in a linear manner, which will produce high volume in the system, and it will test the availability or reliability in the system. On top of that, we have introduced chaos handlers as well, because these chaos handlers are the ones which will make sure on the availability of the services. Since connected platform is a very critical platform in terms of performance engineering, so we need to be very sensitive in this area to validate it for its reliability and availability. And hence we have introduced chaos. So how chaos works is we create the YAML files, and we deploy those YAML files in the test service cluster, which is also known as application service cluster. And the work of this chaos handler is to produce chaos in the overall application. For example, every 30 seconds it will kill the pod, and we need to check the resiliency of the service or the request being sent from the end user. For example, if I am a user of connected vehicle platform and I'm sending a battery charge status or remote horn light service command, then that service command will be hitting to the application service cluster, and before that the chaos cluster will come into the picture, which will kill the pods on which the request was going, and we need to check the resiliency of that request. So this is how the chaos handler works, and we have various type of chaos which help us to understand the system robustness and reliability in various different conditions. And after that we have a report generation mechanism, because it is very difficult to fetch the details of CPU and memory and other stats of availability using direct monitoring tool. So what we have done, we are using Telegraph, Prometheus and Jarvis integration, so that we can run the KQL, which is Kusto query language at the back end, which will produce the result and which will fetch the result using Telegraph and Prometheus and present the data in the consolidated form, which is a report generation. Before that, we are using load runner. So load runner is not a performance testing tool here. It is a Gatling tool, which is an open source tool available in the market, and we use high charts to create the dynamic graphs in the Gatling report. So all this integration is helping us to run the high load in the system in terms of API executions and also in terms of telemetry executions and achieve the maximum. So to use this framework, we require certain prerequisites, which starts from Docker, Kubernetes and microservices. If you look at this, I am trying to make you understand in terms of the benefit of having your application deployed on the virtual machine versus containerized applications. So if you look at this, we have three virtual machines which has app A, app B, app C, and we have containered applications which has app A, app B, app C, app D, app E, app F, and they are using host operating system, whereas the virtual machine uses guest operating system. So containerization is always very helpful to deploy the microservices, and they are producing you an optimized solution, because in the connected vehicle platform we have IoT, we have event hubs, and we have services which are connected to the smart cloud, and they are generating continuous stream of data in the system, and you never know how the volumes will increase in the production. So just to address those, containerization is one of the important criteria which while designing the architecture we have set, because it has more feasibility to scale up. If you can look at this, in case of virtual machine, we have total memory of 16 GB, which is having further connections of VM1 which is having 4 GB, then we have VM2 which is having 4 GB, and VM3 which is having 6 GB. So memory used is 9 GB, memory wasted is 7 GB. Now if you come to the Docker case, you have total memory which is having memory of 4 GB which is being used by the app 1. Then again we have memory allotted 35 GB, out of which 3 GB used by app 2. Then again we have memory allotted 10 GB which is being 2 GB is being used by app 3. So only 9 GB memory utilized, 7 GB can be allocated to a new container again. So this is how it works. But in case of virtual machines, if you can see, 7 GB of memory is blocked and cannot be allocated to a new VM. So that's the problem in the virtual machines case. Further going on the prerequisite side, we have nodes and the respective pods. And pods are obviously they are scaling on top of each node, so every node has a node. You can consider it kind of a virtual machine on the cloud, and on that the pods are getting spawned based on the production volumetrics or the execution of the test framework. So this is a typical architecture where service A and service B, they are communicating to the system, and we have respective pods like pod 1 and pod 2, which has a replica set in terms of pod 3 and pod 4. This slide is presenting an evolution of the applications in the market. So if you look at the slides, it shows monolithic application to a transition to microservices application, which is again Docker, and then now it's K8 as it is Kubernetes. Learning services, you can see the flow, how the source 1 is received the events, which is again going to the multi queues, and then we have on and process specific queues which are going for a queue 1 to get the process, which is again processing the events which are coming, and then we have persist events and downstreams. The data, that's how the data originates and get executed in application cluster on the Kubernetes kind of architecture. This is about the chaos. So we have a cluster chaos, as I mentioned earlier as well. So if you look at this, pod failures in a specified interval is memory drain. Then we have network unplugging and replugging. This is something I have wrote for what all you require to use this framework. So these are the few points which we have mentioned, like should be able to pump in a lot of events through API or telemetry using cloud to device or device to cloud, should be able to test the APIs at scale, ability to introduce chaos within the application cluster, collect metrics, aggregates an application cluster, collect metrics on the test runner, which was a load runner in our case, provide consolidated report and application metrics and test run metrics, ability to reset and apply different application levels, ability to run a test scenario with and without chaos, because before jumping into the chaos we need to make sure like the application is running and stable with the multi-user, so the load can be performed in the application. Then finally we have built the open source model for easy adoptions of different services. Then test manager, then responsibilities of the test manager which we are using in our framework is for reading all the test, starts the test and watch for jobs to be completed periodically. Meanwhile, fetch and log and upload the app cluster metrics while test is running. Wait for all the instances of the test to be completed, because we are running a typical multi-service scenarios, like as I said, like we have cloud to device and device to cloud communication. So device to cloud, we have a lot of services which are running. Similar way, we have a lot of commands running from the cloud to device. So start and wait for aggregation task. after test has completed. Check if there are more tests and repeat to exist. This is a flow of test manager. We have written configuration files, which I will be showing you in the subsequent subsequent PPT next slides. Like it starts from reading the configuration files, and then we have simulation configuration list on which it will read all the data and then deploy the chaos to the application microservice cluster. Then it will start the jobs, and then it will wait for the jobs to complete. Once the job is completed, then it will stop the recording matrix and remove chaos from the app microservices. After that, it will aggregate all the jobs, wait for the jobs to complete, and again, if more items, then repeat, else exit. So that's how test manager works. Then we have storage clients, on top of which we have test pods. Matrix manager is fetching the data from the various system, and then it is aggregating for reports. We have test runner implemented using K8 Node.js client. So when I say Node.js client, we are deploying jobs to test cluster, after reading the configuration files, which have all the configuration details available for the Node.js. Waits for jobs to finish. This achieved by periodically checking for status of jobs in every 20-second intervals. So then after that, it proceeds for all the jobs to get completed state, and then the deploys aggregation jobs. Waits for aggregation jobs to get finished. Similarly, we have metrics reporting implemented using K8 Node.js client and metrics servers. These are the details for the same. Then we have chaos handler. As I explained earlier as well, we have types of chaos handled, in which we can take example of pod chaos, network chaos, and more supported by chaos mesh. So chaos mesh is a community, and we are using different type of chaos from that community. There is a scenario with pod chaos configuration files, in which you can define the scenario, duration, the number of pod failures, and in terms of the parallelism, like how many number of nodes you need to keep. There's a test configuration YAML file, which will get you all the details of how the parallelism will be maintained, and the overall Gatling configurations, and the image which you are going to create and push on the Docker. This is for the aggregation container. This is again a YAML file which the test container will be using, and which will upload the results on the storage. So how to use this? So we have a clone available on the GitHub, and then you can use that, and you can create the images and push that using Docker, using DevOps pipeline, and then deploy using pipeline rollout these specifications using DevOps, which will run the tests. These are the manual steps which I have mentioned in the slides. How the deployment of the test managers takes place. So it pushes the test manager Docker image to the registry, the container registry. Then we have pipeline which pulls the registry and deploys it onto the AKS using shell script. Node.js app starts on the K8 cluster, which is a Kubernetes, which starts the applications basically. So then we have metrics for reporting, like Gatling built-in request response. It is a common tool which we usually use. Then we have resource utilization for K8, which will again we are using Telegraph and other options like Taurus now, and of course we are using Helm chart to do the executions. This is a typical monitoring framework which we are using, which contains InfluxDB, Grafana dashboard, and then we have data collection base. PSR means performance scalability and reliability statistics report. So once the application is there, we have a metric collector and formatter which will get the data from there and then collect the metrics logs. Based on that, there will be aggregator which will form the data. Then it will have an aggregated status. After that, it will generate the report, and the report looks like in the final flow diagram. This is how we collected the format metrics. So we have different jobs which are running, and we have these jobs are running, and it is using CPU cores, corresponding memories, and memory percentage. Aggregate status. Then we have aggregated stats, where we have application cluster and non-app clusters like Telegraph and Prometheus and other non-app things which we are using. So it provides the consolidated one. We have rich HTML based reports from Gatling, as we all know, and we are using K8 matrix for the details. So this is about the summary graphs, various graphs which we are using metrics monitoring, and that is going to fetch the data, and we are using high charts to present the data on the system and monitor it. So future plan we have for IoT integration monitorings, which is not in place as of now. We are using App Insights to do the monitoring for the IoT, because we have IoT devices in the connected vehicle platform, which is very important actually. Telemetry matrices, which we are anyhow capturing via Kusto log, which I have shown earlier. And finally, we have Event Hub monitoring as well, which requires a dashboard, which we have created in Data Explorer, which is an Azure Data Explorer, and which uses Kusto query at the backend.
Thank you, Raman, for this this journey into the future, connected vehicles, right? That's good. That's definitely one of the things we're looking forward to in the next years. So looks like we have a couple of questions. First one up. So complex environment. There's several smart vehicles, smart devices in the vehicle connected to the cloud. What are the top 2 or 3 performance challenges you guys faced in real life so far?
Yeah, so that's a very good question actually, because whenever we talk about multiple devices which are concurrently sending a telemetry to the cloud, so performance is very important in that case, and the unavailability of the services, because of the firmwares are not updated in the devices which are present in the system, or lot of stress, like the volumetrics which are hitting to the various components, because it is a complex architecture and we have a lot of components, and individual mapping of the performance tuning of each component should be mapped all together. So the throughput, we say, so suppose we have component A and component B, so both the components should maintain the same level of throughput, in terms of, because it is a continuous telemetry. Even the vehicles are stopped, and you are not sending any telemetry by your own. There are automatic updates which are going, and communication happening to the cloud. So yes, so we saw a lot of unavailability at various integration points. Those were the major performance issues which we faced. And yeah, of course, for that matter, we need to make the system more resilient, retry logics, and keeping the orchestrator functions, because I work in Microsoft, so we have durable functions, Azure durable functions to orchestrate the request. So these were the major issues which we identified and we fixed also.
And I think you mentioned, you guys, the scale today is about 50 million vehicles, so that starts to be sizable, right? And I guess the question is, I assume that it's going to be a steep ramp up as more and more people move to the newer cars. So
yes, of course.
It's going to be in the billions, right?
Yes, I know. Yeah, that's correct. The challenge is like every year. So we are doing the capacity assessment as well. Suppose we are in 2021 and we are targeting for 2023. The volumetrics is from 10 million at 2021 is going to 100 million in 2023. So that kind of a steep we have. And yeah, you need to define the capacity is a major right criteria here. So yes.
All right, let's see. Next question up, I think, was around service performance. I think service performance definitely is important to have, but I was wondering if you guys gave any thought to the device performance. So, for instance, what happens if I'm driving my car through a tunnel? There's no connectivity. Is my device going to get into a loop and basically prevent me from driving, or you have some
Uh,
safeguards?
yeah, that's again a very good question. Actually, these are the real time challenges which we have been facing, and we have fixed also at some level. The device's performance matters a lot when we talk about the connected vehicle platform, because you need to enable a lot of service in which are integrated to the cloud and to your mobile phone, or any device which you are using to connect to the vehicle. So we do the firmware updates. We keep updating the firmware updates, and we use campaigns. So it's not just about updating. Your vehicle is coming to some center physically, and then you are updating those firmware. Indeed, we send a services which are keep checking the device, they are updated or not, and based on the even we send the patches via service itself to each device, and validate like they should be updated with all the optimizations we have been keeping for synchronization between vehicle and the device. And this entire thing we conduct using campaigns. We call it a campaign. Suppose I need to update for a particular service to a device, so I'll be sending 50 million vehicles. I'll just take that 50 million vehicles as my parameters, and then I'll be sending those firmware updates to those using this campaign, and the solution. So that's how we work. But yeah, it is always a case. But yeah, we have optimized a lot, and we have improved performance a lot. It is seamless at some level. Yeah.
Yeah, it's definitely an important part of someone's life. I would say sometimes
Yeah.
more important than just an app on your phone.
Yeah,
Um,
that's correct.
okay, let's see. Next question up, I think, was just about the performance framework. This is more about stress testing framework, right? I was wondering what kind of monitoring alerting do you do in production?
Yeah, that's like it's, we can say stress testing, because the volumetrics itself is very high, the telemetries, and you have IoT hub, in which all the devices are already registered, and as soon as your device gets wake, so there is a wake up call goes. So again, there will be a peak time for that for that particular IoT hub. So a lot of telemetries will go. So that peak we need to address by doing this kind of survey testing, the stress testing. And why we do, because you need to the availability metrics, which is an important criteria. Like I was telling, like SRE integration is very important here. You need to check at every integration point. We have gateways, the authentications, a lot of two-factor authentications, and the service authentications. All those needs to be addressed, and every gate we do the that production level executions. So this is important in that works. And the second part of question is like what kind of monitoring we are doing in the production. So production, we have created a dashboard which we are already running. They are for Azure Data Explorer, and in the open source world we have other kind of dashboards available. But what we do, we keep collecting the logs. We have put the instrumentations, the major instrumentation inside each integration point, and then we are monitoring them. The customized dashboard, basically. Yeah, that's how we are working. Yeah.
Thank you for that. Um, you've generated lots of questions. So next one from Stefano about application configuration to ensure performance and reliability on Kubernetes. What kind of how did you deal with that particular problem? Container resource limits
Yes.
requests.
Yeah, so that's For we have AKS application cluster where we deploy the services. For telemetry, it is altogether a different handling. But for APIs and the services, yeah, the configuration parameters are very important, and that's how we do the orchestrator. Like we need to integrate the resiliency in the system, and what we do, we always keep the dynamic configuration files, which are keep updating. Mostly we use YAML file I shown in the video as well. So those configuration files are very important, which we keep in the key vaults, and those are getting updated via key vaults in Azure. So that's how we handle.
Great. And Stefan will be talking later about his tips and tricks on Kubernetes, so I'm sure you'll have questions for him as well. And last question I had was just about the Chaos framework. So everybody when they hear Chaos, I think about the Chaos Monkey goes in production. Yours seem to be a bit more tamed monkey. Stays just in testing. Is that right?
Yeah, that's correct. So majorly the chaos integration is in the application clusters environment where the application is deployed and we are running the YAML files there. And in terms of in the production, so in production we have different ways of testing, but we are not directly using monkey testing and other things. But yeah, in the just before the production environments, the STG environments we call, where we do all these executions and make sure like the services should be reliable and resilient. So that's how we do for this framework.
Yes. Superb. Raman, thank you for the great talk. Thank you for surviving our barrage of questions.
Thank you.
And looking forward to more chatting with you more at the panel discussion.